Hi everyone, welcome again to the screencast. And today we're trying to solve this problem from 1.23. A firm produces juice in 1 liter and zero point 0.5 liter bottles. The machinery involved can produce up to 4,000 liters of juice per day, and the packaging department can handle almost 7,000 bottles per day. Market research indicates that no more than 6,500 of the zero point 0.5 liter bottles will be required by shops per day, and demand for 1 liter bottle will not exceed 4,000. At least 4,000 bottles needed to be produced to keep the workforce occupied. There is a profit of $10 on each 1 liter and $5 on each of zero point 0.5 liter bottle. The question is to maximize profit. So maximize profit. It's similar to the one we just concluded some time ago. Would you want to try this question? You can pause the video and see if you can solve it. Then we'll come back to it. Your task is to set up an LP expression for this problem. All right, so we can put a stop and come back. Okay, if you're ready to go, let's go. Now, we need to understand what the design variables are. We also need to know to understand what they're really asking. It says maximize the profit. How do we maximize the profit? But if you look at the last sentence here, he says there is a profit of $10 on each 1 liter and $5 on each of the zero point 0.5 liter bottles. Now watch this. So the amount or the number of bottles that I sell and the content in them that I sell will actually determine my profit. Is that correct? Am I communicating? Yeah, I think so. So then what I then need to maximize is the number of bottles based on all the constraints that are involved in the question. So the first thing we need to determine are the design variables. So we'll say, to get that, we'll say let me just change this back to black. So say let the number of 1 liter bowl be x1. Let the number of 0 0.5 liter bowl be x2. Straight away, without any hassles, you have succeeded in defining the design variables. So design variables equals x1 and x2, right? Okay. From the last sentence, we can come up with the objective function. So my aim, it says from the last sentence, it says there is a profit of $10 on each 1 liter size bowl and $5 on each of the 0 0.5 liter bottle. So I can say right here that 10x1 1 liter plus 5x2. This is what I'm trying to maximize. Unlike the other one, the other question that we just concluded, there is no cost here, right? So I don't need to bother about that. So straight away, I can write f x1, x2 is 10x1 is 5x2. This is my objective function. OBGN. You should represent it with this F here. Okay, now if you go to the second statement, the first statement, right? The first statement on the question. Let's look at that statement again. A firm produces juice in 1 liter. Now, juice is what the container is filled with, not milk, but juice. Now, you need to note that. And you need to note that if we make an assumption here that assume that the volume of juice is the same thing as the volume of the container, right? Yeah, we can actually assume that. So it says a firm produces juice in 1 liter and 0.5 liter bottles. The machinery involved can produce up to 4,000 liters of juice per day. Up to 4,000 liters of juice per day. Straight away, I know that is telling me that even the content of the juice, right, should not be more per day, should not be more than 4,000 liters. Okay, so I can say liter of juice constraint, liter of juice constraint equals, because it's an inequality, that's G1, I can say X1, X2, and I can say 1 liter, X1, 1 liter, because I'm looking for the number. Now, the number of liter of bottles, the number of 1 liter bottles produced altogether will give me the liter of juice in 1 liter bottle per day. I don't know if that makes sense. So you gather all the 1 liters together. The content of all of them is the total amount of liters produced per day. And all of them together, both X1 plus 0.5 X2 should not be more than 4,000 according to that statement. Okay, I mean that's pretty straightforward. But the packaging department also has some issues here. So if you go back to the question, right, just let's go back to the question and see. He says here that right here, of juice per day, and the packaging department can handle at most, so you can't go beyond that. Okay, at most 7,000 bottles per day. So packaging, that's some packaging constraints. So packaging constraints, that equals to, let's call that G2, X1, X2, and that's what now? So we can say, X1 again plus 0.5 X2. No, watch this. What is X2? Let's be careful here. Okay, sorry about that. Let's be careful here. What is X2? That's why I said earlier on that this is the most simplest and easiest part of optimization. You have to be careful, otherwise you miss it. Look at it. Let the number of 0.5 liter bottles be X2. So that's it. X2, which is the number of 0.5 liters, should not exceed 7,000. I hope that is clear. I hope that's clear enough. Okay, cool. Let's go back to the question. Then he said, market research indicates that no more than 6,005, no more than, so it shouldn't be more than that, 6,500 of the 0.5 liter bottles will be required. It means demand here is saying we don't need more than 6,500 bottles per day of 1 liter. And and 0.5 liter bottles will be required by the shop per day, and the demand for 1 liter bottles will not exceed 4,000 per day. So these are demand constraint, means produce whatever you want to produce, but we don't want more than 6,500 of 0.5 liter bottles, and we don't want more than 4,000 1 liter bottles. So I can just say demand constraint, and that equals let me call that G3 now, x1 x2, and I can say this is positive here. I can say, so let's start with the let's start with the 1 liter bottle constraint. So x1 is less than or equals to 4,000. That's what the demand says. And straight away I can also say here that G4 x1 x2 is for this 0.5 liter bottle, that should not exceed 6,500. Okay. All right, so let's go back to the question. At least 4,000 bottles need to be produced, at least, which means it could be greater than that, but it should not be less than 4,000. Does that make sense? At least 4,000 bottles need to be produced to keep the workforce occupied, get the paycheck at the end of the month. It has to be that. So then production, that should be production constraint. Production constraint here. Let's call that G5, X1, X2, and see if the sum of those bottles could be greater than 5,000. Is that 5,000 or 4,000? Let's go back to the question. 4,000, 4,000, 4,000. Sorry about that. So just put that in there. 4,000. Cool. So one kind of thing with this problem is the resource here is the number of bottles that needs to be produced. You cannot have negative bottles, right? Negative bottles, no. Neither can you have 0 bottle. Well, you can have 0 bottle, but you can have, it has to be greater than or equal to 0, not less than or equal to 0. So what I'm trying to say in a nutshell is that x1, the number of 1 liter bottles must be greater than or equal to 0. Okay, and x2 must also be greater than or equal to 0. These constraints are critical, even though it's not stated directly in the question. And that's important for us to know, because you can have a negative bottles, right? You can't. So that is it. And once you set up the equation like this, then we can go to MATLAB to solve them. Now this is the end of the screencast. I hope you enjoy it. If you do, please remember to subscribe. If not, that's also fine. Just keep following. Thank you.